we will start with the chapter electrostatic potential and capacitance. Now this is the second chapter of NCERT. So the chapter is electrostatic potential and capacitance. So this is the second chapter of NCERT book. First chapter already we have finished. Hope you have covered all the assignments and NCERT exercise. This is the second chapter. Now before going to electrostatic potential and capacitance, do you know that we know about the conservative forces, electrostatic force and gravitational force? Certainly we know that there is a gravitational potential energy, electric potential energy, there is a gravitational potential. So in this chapter we are going to know about the electrostatic potential, energy and then capacitance. Just I will give you a comparison between the two basic phenomena. One is related with the gravitation and the other is the electrostatics. Just we will relate it. We'll see that how the mass and the charge are analogous to one. In the gravitation, the first force was between the two masses. Remember? M1, M2, and this force was gravitational force G M1 M2 by R square. Here, if you see, there were two charges. One was Q1, Q2, and the distance between them is say R. So the electrostatic force was what? K Q1 Q2 by R square. We have gone through it. So this is the first thing which we see, that both are the fundamental forces and both are inverse square law, both are conservative forces. The difference is between their constants. Okay, the second thing which we know about the mass is that if there is a mass and then at point P we can find out the gravitational field intensity. And remember that gravitational field intensity is Gm by what? R square. So R is the distance. Similarly, you know that here if there is a charge Q and you want to find out the electric field intensity at point P, so it will be outward at R distance. It is what? KQ by R square. And if there is a negative charge, the same thing we see here, point P at R distance, it will be towards the negative charge and the magnitude is same, KQ by what? R square. Why? Because the gravitational force and electrostatic force, there is a difference. The electrostatic force is attractive and repulsive both. Okay. So this is the intensity difference. Now the third one is the gravitational potential. If you remember, this is mass M at R distance. In 11th class you have gone through the gravitational potential was minus Gm by R. Remember work done in bringing a unit mass from infinity to that point. So at this point this is similarly, if you see that if there is a charge, and we are going to discuss this now, that R distance at point P, you want to find out the electrostatic potential, it will be what? KQ by R. So replacing M by Q. But there can be two type of potential. Minus Q will produce what? It will be minus KQ by R. So potential are again of two types. One is positive and another is negative. And then the last thing which we have gone through, that if there are two masses M1, M2, then certainly we can find out the potential energy between them is minus G M1 M2 by R. Here the same thing we are going to discuss is that if there are two charges Q1 and Q2, what we can do is that we can find out the electrostatic potential energy is that UE is what? K Q1 Q2 by R. So this is gravitational potential, this is energy. So these are the basic differences between gravitation and electrostatics, and then we will carry on what is exactly the electrostatic potential. Potential is defined. Now electrostatic potential. If I talk about what is electrostatic potential. Now if you remember that when you have gone through a topic in class 10th, what was potential? Work upon what? Charge. You remember? And this work was Q naught into V. Now if I ask you what is potential, SI unit is what? Volt. So 1 volt can be written as 1 joule by 1 coulomb. So this is the SI unit. SI unit is volt, or SI unit can be written as joule per coulomb also. These are the SI units. Okay, and this is work. You remember work done per unit charge was gravitational potential. Here it is electrostatic potential. Now the concept behind this is that what I told, potential are of two type. If you see electrostatic potential are of two type. Remember, one is positive potential. We say positive potential. And one is what? Negative potential. Remember, positive and negative potential. Even if you see that if there is a resistance and there is a battery, you know that there also we see the two terminals. One is positive potential and negative potential. And because of that only the potential difference comes. You know the potential difference. So one is of positive potential plate and second is of negative potential plate. So this is how you remember V equal to IR. So electrostatic potential is defined like this. Now how this relation has come, I will talk about the relation also, that how the potential difference and potential are related. If I ask you that there is a charge Q, okay, we are talking about potential difference, and there is another charge, say Q naught. Now it is placed at some point from here, and this is another point, and we are taking this body from A to say this point B. Now you know that, remember there is a work done, and work done is, you remember, integration A to B, and it is F dot dr, the force, work done in bringing a force, and you know that we are taking this charge from this point, and Q naught is less than Q. So this force is basically the external force, and you know this external force is opposite to the electrostatic force. So what we can see is that A to B, we are taking a charge from A to B, can also be written as F E dot dr. In place of F, we have written minus Fe. So minus will be R. This is the work done. And you know, work done can also be represented as, you remember, in work energy theorem, change in kinetic energy. Here we can say change in potential energy. So delta U, and it can be written as UB minus UA. This is the work done, and this is the work done represented. You can even represent UB minus UA as this. So how this work done is represented? UB minus UA. And this is the work done from what? A to B. So this can also be written as WAB. Okay. So this is how we define it. And remember one thing, that VB minus VA, this is the potential. VB minus VA was defined as work done per unit charge. This is the potential difference. So potential difference from what? From A to B, final potential minus initial is work done upon per unit charge. And this is the way how we define work per unit charge. So potential difference is like this. Now how we define potential at any point? Okay. So potential at any point, remember the definition? Remember the definition of gravitational potential? What was gravitational potential? Gravitational potential was work done in bringing a unit mass from infinity to that point. Okay, the same thing we define now. Electrostatic potential. So electrostatic potential we are going to define, and electrostatic potential is defined as what? In the same way, electrostatic potential at any point, electrostatic potential at any point is defined as the amount of work done, the amount of work done. You remember the amount of work done in moving in bringing a positive charge, in bringing a positive charge from infinity to that point against electrostatic force, against electrostatic what? Forces. So this is how we define. So ultimately electric potential, if we say V is the electric potential at any point, so V will be work done upon what? Charge. So this is how we are going to define the electrostatic potential. Already we have discussed the SI unit, and if there is a charge say of 2 microcoulomb, and I am saying what is the potential at 2 centimeter. So simply K Q by R, this is the actual formula. What is K? Is 1 upon 4 pi epsilon naught Q by R, and this is actually a scalar quantity. So can I calculate it? Yes. Do you know the value? 9 into 10 to the power 9. What is Q? 2 into 10 to the power minus what? 6, and this is 2 centimeter. 2 into 10 to the power minus 2. So you calculate it, it becomes 9 into 10 to the power, and it will be 10 to the power 5 watt volts. So this is the potential. And remember, it has no direction. It's a scalar quantity. So electrostatic potential can be defined in this way. Okay. So this is KQ by R. Now how it has come, I will explain how electrostatic potential has come. So we have first derivation related with electrostatic potential. We will discuss it. And that is electric potential due to a point charge. So we will talk about electric potential due to a what? Point charge. Due to a point charge. So this is the first derivation, and already we remember the formula. What I wrote is 1 upon 4 pi epsilon naught Q by R, K Q by R. Remember single R. So we are going to define it. Say there is a charge, say here it is a charge, say a charge Q, and there is another charge, say here Q naught, and we are bringing this charge from infinity, and right now this charge is at A point. After some time it will be at B point, and this is the dr distance. Okay, and this is the charge, and Q naught is less than Q. So we are taking a charge from A to B, and remember you calculated gravitational potential, same as this. So we know that let dW is the work done. dW is the work done, okay, in taking charge from what? A to B. Right now we are taking, and this distance, say this is point, this distance is R, and this distance is say what? X. So we are going to take it from what? Infinity to B point, and this is X, so we can take it dx. So work done in taking a charge from A to B, and you know what is the work done? dW is what? F dot what? dr, and what will be the net work done? You know that W integration of F dr what? cos 180, and this is from infinity to this distance, so r, and remember what it will be, minus f dr from infinity to r. Now this f is actually the electrostatic force. What is the electrostatic force? K q q naught by what right now? What is the distance? It is x. So we will take dx, not dr, dx. So f dx, so it is x square. So ultimately it will be minus what, infinity to r, q naught by x square dx. And remember, q naught will be what, out, and it will be dx by x square, what, infinity to r. You remember you have done same thing there. And finally w minus q naught. What is dx by x square? You remember it is minus 1 by x infinity to r. So w minus will be plus, and q naught 1 by x infinity to r, this minus minus, and then finally it is 1 by r minus 1 by infinity, and 1 by infinity is 0. So what is that? q naught by what? R. So this is the concept, and this constant is coming here. So it is k q naught by what? R. So ultimately, if I say what is the work done, so work done has come what? Q naught by R. And what is work done per unit charge is Q by R. And that is defined as electrostatic potential. So this is the derivation related with electrostatic potential due to a point charge. Very simple. You took a charge here, Q naught, and then you know that work done in bringing a charge from A to B, f dx cos 180, and then infinity to r, you integrate it, and then you know that this is the step, this is k, and then ultimately kq. And what is the work done per unit? So potential is defined as work done per unit charge also. So already we have defined this as electrostatic potential due to a point charge. Remember, its electrostatic potential is a scalar quantity. Remember, it has no direction. So this is the electrostatic potential which has been defined. Now, there is a very important graph. You remember that what was electric field intensity? Electric field intensity, say this was a Q charge, and if I ask you what is electric field intensity, you will say it's KQ by what? R square. And if I now talk about that there is a charge, and at this point, what is the potential? Now you know it is KQ by R. So it is 1 upon 4 pi epsilon naught, 1 upon 4 pi, but epsilon naught Q by R square, and it is what? 1 upon 4 pi epsilon naught Q by R. Got it? So that means electric field is inversely proportional to R, and where R square, and the electrostatic potential is inversely proportional to what? R. So there is a graph between the two. The difference is that this is what? A vector quantity as a direction. It's a vector quantity, but this is a scalar quantity. So we can draw a graph between the two, and the graph is very simple. We can draw it, and this is the graph we are going to draw between these two quantities. This graph will be in the same quadrant we are going to draw, and this is VE versus what? R. So this graph is between the two quantities, and now one is this. We are talking about the electric field intensity. So electric field intensity graph is, and the electrostatic potential graph is this. So remember that this is electric field, this is potential, this is electric field. And you know that at some point they are same. When R is 1, V and E are same. If I ask you how, so very simple, E is equal to V, you put R equal to 1. A unit distance, E and V become same. So this is our, this shows that this will be steeper on this side. This is the x-axis, this is the y-axis, because E is inversely proportional to R square, whereas V is inversely proportional to R. So this is the graph between electrostatic potential and the electric field intensity. Now, electrostatic potential due to system of charges. So, electrostatic potential, if there are number of charges due to a system of charges. Okay, due to a system of charges. You can calculate the electrostatic potential at any point and say this is the point P, and there are number of charges given. Say this is Q1, Q2, Q3 and Qn. So these are the charges given, say Q1, Q2, Q3, Q4 and dash 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 Qn. There are number of charges here. So this distance is say R1P, R2P, and this is R3P, and this is RNP. So we have number of charges given and what will be the net potential at this point. So simply you know that potential is a scalar quantity. Again, remember it's not a vector quantity, it's a scalar quantity, and it follows additivity. So if it's a scalar quantity, it follows additivity. So simply potential is what? V equal to V1 plus V2 plus V3 plus dash 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 Vn. So we can add them. What is potential? KQ by R. So KQ1 by R1P plus KQ2 by what? R2P plus KQ3 by what? R3P plus dash 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 KQN by what? It will be RNP. So you add them and you know that you can make it like this, 1 upon 4 pi epsilon naught common. So Q1 by R1P plus Q2 by what? R2P plus Q3 by what? R3P plus dash 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 Qn by what? RNP. So this is what? Net electrostatic potential due to multiple charges. I will give you an example. Say this is plus 6 microcoulomb and this is minus 6 microcoulomb. If I ask you what is the potential at the center. Now see, this is an example. This is a dipole and say this is R and this is also R. What will be the net potential? Do you know? It will be simply V1 plus V2 and it will be, if I ask you KQ, Q is 6 microcoulomb by R and another will be minus 6 K 6 microcoulomb by R. Why? Because it's a negative potential. So net potential is what? 0. So at the center of a dipole, you know that net electrostatic potential is what? 0. So this is V0. It's a scalar quantity. So in this way we have discussed something in this video. So this was the first video. Thank you watching for this video. Regularly watch my videos.